matrix factorization method for dense word vector representation. Let's look into it a little bit. So first, in order to use a matrix factorization method or methods, we need a matrix to factorize. What would we look at? Let's imagine that we have a vocabulary, and vocabulary goes by word 1, word 2, and then we get our word n of vocabulary size, and in such manner we construct symmetric. Word 1, word 2, symmetric matrix with all of the words vocabulary size. What is written in those cells of this matrix or a table? So for word ij, we write here the number of times word I and word j occur in the same context. This is important what context is. If we're doing document analysis, words inside of documents, then this matrix is not symmetric, and we can have word 1, word 2 through word n, and then document 1, document 2, document. Does that sound familiar? Does it sound familiar? Where how many documents we have? We have k documents here. And okay, how many times does word 1 occur in document 1? 3. How many times does word 2 occur in document 2? And we fill in this matrix with counts of how many times a word occurs in each of the documents. That's very similar to what we were doing in a bag of words representation, if you recall. But we can also have word by word matrix and a corpus of text. And in this corpus, we can look at all of the strings and look at all of the context, which is nothing but a linear sequence of words of a specific length. We could say even variable length. A context could be a sentence. Does a word I and a word j appear in the same context? Or how many times word I and word j appear in the same context? In the same sentence, or sentences could be short, could be long. Let's define a context as a floating window of size w. So the context could be w equals 4, or w equals 5, or w equals 6. So look, slide a window, and for each of the words in the vocabulary, fill in that matrix with values. Good, right? And the values will be just the counts. How many times this word and that word I and j occurred together within the same context for all possible contexts. Nice. But the only problem is the co-occurrence of stop words, like articles, like and other words will dominate the table. The values will be high because they will co-occur with all of the possible words much more frequently than any other words, and the co-occurrence is not semantically meaningful. So one thing to do is to just remove the stop words up front, but we don't always know which are the words, not just the stop words, but maybe there are other words just like too frequent in some context. If we're looking at corpus of some subfield, scientific subfield, there could be some terminology that is meaningless, but it's frequently occurring, and situations like that. You should know by now what to do in this situation. We already covered that. It's TF-IDF. So fill the table with TF-IDF values instead. Because our TF-IDF value here is about co-occurrence of word I in context J, but we can just treat I and J be the words and can normalize the co-occurrence relative to the context, the same as we've done normalization with IDF relative to the document. So this D could be context in which this particular word appears, or when they share the context. This is not the only way. Another way that is easier, or not easier but simpler to explain, is to use point-wise mutual information, or PMI. So PMI tries to estimate if the words occur, if the word X and Y or the words W and C occur more than if they were independent. So what you see here is the ratio. This is a binary logarithm. This is their joint occurrence, and this is their independent occurrence. And we are looking at the ratio of joint distribution, and two variables are independent if their joint distribution can be represented as a product of their marginals, then the variables are independent. That's what we're looking at. When this holds, this is true, the ratio equals 1 and the log of this ratio is 0. So pointwise mutual information for word 1 and context 1, or word 1 and word 2, because word 2 now defines our context for word 1, becomes 0. So let's see how it works. Now PMI is the ratio, as you can see, is the ratio of this conditional. We can just divide through by W and get the conditional, and marginal for the context word. And context, how do we estimate that? And that's what we learned in our maximum likelihood estimation classes when we were going through maximum likelihood estimation of coin tosses, if you recall, and maximum likelihood estimation for spam detector, filter detector. It's practically the same. Probability of context word is count of the context word relative to the number of total words in the corpus, and then we need to estimate this conditional, and it is the same as before. Joint is probability of the count of when those pairs appear to the size, and probability of word 1 is the number of occurrences of this word normalized by the size, and then plugging all of that back into the formula, we get that pointwise mutual information is nothing but the count of when word context word C and our focus word appear together times the size of the corpus, and then count of context word, just number of times it appears, times in the corpus, times count of the focus word, number of times it appears in the corpus. All looks good, right? But wait a second. PMI, pointwise mutual information, ranges from -infinity to infinity. So it is 0 when the ratio is 1, but if the ratio is less than 1, it's negative, and it's more than 1, it's positive. It's because it's the log of the ratio. But the negative values are problematic, right? Things are co-occurring less than we expect by chance. That's what negative value would mean. And they're unreliable. Those negative estimates are unreliable without enormous corpora. Imagine word 1 and word 2, whose probability each is 10 to the minus 6. Then hard to be sure if probability of the joint probability of those words is significantly different than 10 to the minus 12. Because that's what we're estimating, 10 to the minus 6 times 10 to the minus 6, and then those are tiny numbers, and we're getting into numerical problems potentially. And otherwise, it's not clear whether people are good at unrelatedness. Just understanding whether those two words are unrelated or not is not that. It's very hard to reason about. So let's try a hack. Let's just replace negative PMI values with zeros. And if we do that, then we get our definition of positive pointwise mutual information, PPMI. So if your PMI is greater than 0, then just use this value, or use 0 otherwise. So now you see that frequent words and stop words are normalized away in PPMI table. So we solved that problem, but we introduced another, of course, no free lunch. PMI is biased towards infrequent events. So if we have some words that are very rare, they will have very high PMI values and PPMI, of course. So the two solutions. One solution is give rare words slightly higher probabilities, just fudge them, or equivalent solution, use add one smoothing, which has a similar effect. Add one smoothing for our PMI will be so we have our standard definition. What we'll do, we add 1 here and add size of the corpus here, normalize it by the size of the corpus. Okay. Now let's look at a fun example of how those tables could be interesting just by themselves. So we've constructed a table for all words in the corpus, and the value in each table is just a conditional probability. Say for what's the probability of word solid occurring together with the word ice when look at all of the phrases that contain ice, or all of the contexts that contain ice, and see the chance of occurrence of the word solid. And the same for gas, water, fashion. If we look just above this line, those numbers are kind of small, it's unclear. 3 and 2.2, are they different or are they compatible? But the fun part happens if we look at the ratio of conditional probability of word k when ice is present, and conditional probability of word k when steam is present. Well, we have 3 states of matter, right? Let's forget about plasma for now. So solid, liquid, and gas. So that's what we're considering here: solid state of water and gaseous state of water. And we want to see if our model knows a little physics. And look what happens if we check the ratio of solid word solid when it's present with eyes, like what is more likely to eyes to be solid? Word eyes. Remember, the model supposedly doesn't know the meaning, but it's surprising what it gets. If word K is more likely to correspond to the eyes, or then this ratio will be higher than 1, and if it's more likely to correspond to steam, it will be lower than 1, or just low ratio. And as you see here, the word solid is more likely to go with eyes, so the eyes must be solid, are embedding things, quote unquote, because probability of its being a gas, or the ratio it's being gas, is very low, because gas goes more often with steam than with ice, although there is dry ice, of course. Be careful not to inhale that CO2. And interesting, we haven't done anything fancy to our table. We just looked as intended on the neighborhoods, on the contexts, few words apart. I don't remember how many words were in this context in this particular example from the glove paper, global vector representations. But nevertheless, it's like a table already gets us, or a matrix, it already gets us a lot of information. If we look at the ratios, we see that just word co-occurrences, as Wittgenstein predicted, can tell us a lot about physics, or rather human use of these words do correspond to their physical meaning of states of matter. Fun, right? So another case of using the another case of using I wonder another case of using another case of using tables like that is latent semantic analysis. If we construct a matrix, word co-occurrence matrix for documents and words, we can reconstruct the block structure of that matrix and extract topics, semantic topics, without even encoding the topics. Look, for example, this set of documents, clearly after rearrangement of the word co-occurrence or word document co-occurrence matrix in latent semantic analysis, LSA, we see some groups of documents and words emerge, and we see that words illegal, immigration, amnesty, aliens represents some kind of group of documents, and another group of documents is represented by air pollution, power, environmental, and space launch boosters are in another group. And so we found latent semantical groups, how the documents are grouped together by their meaning. And that is, we haven't done anything to the matrix yet, just counted the co-occurrences, or normalized them with using PPMI or TF-IDF. So what if we look at this matrix of the co-occurrence matrix? In this example, m is not equal to n, and if m is the number of words and n is number of documents, then it's not a symmetric matrix. But we can also say it's an m by m, or words by words matrix. So vocabulary size by vocabulary size matrix, that's fine. But if our matrix is huge, if our vocabulary is 10,000 words, it's a 10,000 by 10,000 word matrix. Is it really informative, every word co-occurrence with every word is contains information that we can't get rid of, that is not noise. So we operate under assumption somewhere from the beginning of our introduction to machine learning first classes. We operate under assumption that the word has an underlying sparse structure or lower dimensional structure. So if we do that, we can represent, and if we continue that line of thought, we can represent our word co-occurrence matrix, whether even though I say co-occurrence, but it could be, as I already said, TF-IDF or PPMI or any other measure of word similarity that you decide to use, semantic similarity. It is somehow, in all of the senses, captures context, like whether they come in the same context. But we can, if we assume that this matrix has low rank representation, there is a hidden lower dimensional space where the word semantic lives, then we can construct this matrix, reconstruct it as a product of two m by k and k by n, and again m could be equals to n matrices. And if we if we do that reconstruction, or deconstruction actually, factorization, then notice the following. We had m words, so J's word now is represented as a dense vector k of size k. Say, just to be specific, k equals 100. So we used to have 100,000 by 100,000 matrix, and we only knew co-occurrence of word I and J. But now we have a dense representation of this word, because even if this matrix is rather sparse, low rank approximation will be dense, necessarily denser, because we will chop off the low or the higher frequencies that can model the zeros. And word I and word J are dense. Their inner product, when this vector is multiplied by that vector in the course of this matrix multiplication, is that value, their co-occurrence. So we're saying that projection of one vector onto another, if we decompose this matrix, so those words that occur more often together, more likely to occur together, will have lower angle than, well, those are this was a bad example. Those are negatively occurring. We're ignoring those because we are working with PPMI. But if a word never occurs together, then so all of these words in this plane are orthogonal to our keyword. Their inner product will be close to zero or zero up to noise, and as you can see that this matrix factorization of word co-occurrences can lead to a vector representation where angle between vectors encodes semantic similarity. Again, back according to Wittgenstein formulation, semantic, the way humans define it, the way humans put those words in the same context. We can also represent our matrix, word co-occurrence matrix, as SVD, singular value decomposition. Singular value decomposition, as you see here, you start with a regional transform, and well, we decomposed our matrix in SVD into a series of transform. One transform is rotation, then rescaling, and another rotation. So V is orthogonal, which is yeah, my naming here is slightly off with respect to that picture. This is U, this is V transpose, and those are our singular values. Then in this case, our word vector matrix will be U times sigma. So scaled, basically scaled version of U. This will be our word vector matrix. Each it will still be dimension m by k. So for each of the m words, there will be a k dimensional vector representing that word, and that's a way to get, and this vector will be necessarily dense. That's another way of using matrix factorization to get dense vector representations based on their co-occurrences. And as you note, each component in this k vector will be scaled by particular eigenvalue. So each component will correspond to certain topic as well. But the point is to note, as in my previous example before, the relationship of the inner product of those vectors with their similarity. The higher the inner product, the higher is their semantic similarity, because the higher is the value in the corresponding cell for the similarity of those two words, I and J, on this figure. So first of all, note that word 1 or 2 inner product can encode semantic similarity, or we want to find such representation of W1 and W2 that their inner product encodes semantic similarity, co-occurrence within the same context, that is. Once we do that, then the space where those vector live should have some meaning, or should have some interesting structure with respect to meaning of those words. And people have been doing it for a while, although again, even SVD for 100,000 dimensional matrix is very difficult, even though lots of algorithms exist, but they're still cubic if you don't use any further approximations. Okay, take home points. Word similarity as co-occurrence within same context. Well, we've covered that in the introduction. Different way to estimate it, but all can be put in a matrix. So the matrix can be low rank factored, and dense word representations emerge as a result of this low rank factorization. Inner product of word vectors encodes co-occurrence or probability. That is important. And another thing I want to bring up is if we have word 1, word 2, they live in some high dimensional space, but they could be, one vector could be this length, another one could be that length. When remember from the course of dimensionality lecture, just to connect all of the dots, when we go to a higher dimensional spaces, well, not infinity, where let's say infinity is more than 20, then all of our vectors, they become to be like they happen to be very close to each other, and it's very hard to distinguish them. So it's a good idea to normalize all of your vectors, or equivalently, instead of inner product, compute cosine between vector 1 and vector 2 in word 1 and word 2 in order to find similarity of those vectors.